Okay, so we're going to take a look at chapter 6, electronic structure and the periodic properties. Ultimately, this is going to look at electrons, how electrons stack in an atom or come together in an atom, and how that leads to different periodic differences, how certain elements behave differently. So we have to start that conversation with the idea of waves, electromagnetic energy, and kind of how all of this connects. So the first conversation we're going to have is about the propagation of a wave. So light or energy acts as a wave. So if you were to drop a stone in the water, that energy is dissipated by a wave being created. Essentially, it moves matter, and you see this little wave, this little ripple that happens. Oh, something similar happens when a burst of light or release of energy in the form of light happens. You get propagation, so you get the wave that is going to go in a certain direction, but ultimately what you have is that ripple is not matter anymore. What it is it creates an electric field oscillation, and perpendicular to that, a magnetic field oscillation, and hence electromagnetic radiation. The electro and the magnet part come from the fact that it's creating a wave or a release of energy in wave fashion. Okay, so we'll get a little bit more into the wave nature of light and orbitals and all that stuff a little bit later, but it's important to understand waves in order to have that conversation. So let's start with the idea of an actual wave. So I'm going to create a wavelength. I'm going to create a wave rather. And one of the most important things to understand is the wavelengths when we're looking at a wave. So from the peak of one to the peak of the other, that is one wavelength, okay? And you can go anywhere you want. You can go from peak to peak. You can go from origin to origin. There's one full wave. Or you can go from trough to trough. That distance right there is going to be a wavelength. So as we would imagine, it is the length of one wave. Typically, the unit that we're going to use is going to be, of course, it's going to be in a distance, but nanometers or meters. We see meters when we're actually dealing with unit conversion and stuff, but nanometers is typically what you're going to see for, when we're looking at the visible light spectrum, which we deal a lot with. Frequency. So frequency, on the other hand, is slightly different. Frequency is going to the wavelength, as we can see in this last equation here, wavelength and frequency are related. So frequency is defined as the number of waves that occur in 1 second. So the unit for this is interesting. So the unit is going to be, so it's per second. So ultimately what this is waves per second. Just like up here, this is meters technically per wave. And this unit is going to be essentially waves per second. Or what we really want to say is it's going to be 1 over seconds, or it's going to be seconds to the -1, or hertz. A hertz is considered an inverse second, or cycles per second, waves per second, that type of thing. So per second, inverse seconds, that's the frequency. Those two things come together when we take a look at the speed of light. The speed of light is 3 times 10 to the 8 meters per second. It's like 2.999, it goes out quite a ways, but 3.0 meters per second. And we can use, this equation right here in order to determine in order to figure out a wavelength from a frequency or frequency from a wavelength. So those two things are in fact linked. In fact, wavelength is inversely proportional to frequency. So if this is wavelength, and this is frequency. And if you take a look at the units for this, a wavelength is going to be in meters per wave times frequency, which is going to be in waves per second. Well, waves cancels, and you're going to end up with meters per second. Okay, so you can rearrange this, of course. So if you want to figure out, well, how many wavelengths, how do I solve for wavelength from frequency? It's just simply C over frequency. If you want to figure out frequency, it's C over wavelength. So again, just a rearrangement of the equation. Okay, good. A couple important things. This is 3.8 meters per second, and this is in vacuum. So this, of course, the speed of light does in fact change when it goes through different mediums. That's how we get the index of refraction and whatnot, but that's an important thing to understand here. So units, yeah, we ignore the wave part of it. And then really quickly, if we're talking about frequency, just in thinking, and we're going to take a look at this on the next page, actually, just in terms of something that has, so if we take a look at this sample wave here versus this sample wave here, it's not the greatest, but doesn't really matter. This is going to have a low wavelength. Sorry, I shouldn't say low. What I should say is a long wavelength. Long wavelength and a low frequency, right? There's fewer waves per second and it has a very long wavelength. So if you have an increased wavelength, you have a very low frequency. The one down here, on the other hand, has very short wavelengths and it has a very high frequency. We're going to see a lot more waves per second. So in this case, we have a short wavelength and a very high frequency. So those two things are in fact related, as we saw in that equation. So how is there energy involved? Well, it turns out that the short wavelengths, again, so this is short wavelength, high frequency. This is going to be considered a high energy. So anything that has high frequency, short wavelength, those are going to be very high energy. And the opposite, these are low energy. On the right, cell phone, microwave, visible light is what we're going to spend a lot of our time in, visible light, and then UV, infrared. So these things have different wavelengths, and the wavelengths vary. I will say for visible light typically goes from 400 nanometers to 700 nanometers on the less energetic end. So with that said, let's solve these problems. Red light has a wavelength of 725 nanometers. What is the frequency of radiation? We're going to go over this in class. X-rays have a frequency of 1 times 10 to the 18th inverse seconds or hertz. What is the wavelength of this radiation? So let's take a look at that and let's solve that one. So before we continue, let's briefly talk about this idea of standing waves. So these are standing waves. Standing waves are if you have something connected at both ends, if you have essentially a string connected at both ends, the more energy it has, the more wavelengths are going to be in between. So something interesting that you're going to see here. So first of all, standing waves. Standing waves are going to contain n number of, n is equal to the number of half wavelengths. Okay, so you can see a half a wavelength. So if we look at just one wavelength, that's going to be one wavelength. Well, a half a wavelength would just simply be that. That is going to be 1/2 a wavelength. And what you're going to notice is all of these have, in fact, that has 1/2 wavelength. This next one has 1 full wavelength. This is 1 1/2 wavelength. And this last one has 2 wavelength. But ultimately, if n is the number of 1/2 wavelengths, this is 1, 2, 3, and 4. All right. So what is the wavelength? So what we're seeing is these standing waves, they're required to have, we can't have, in order to be connected at one end and the other, what we're noticing is there has to be some amount of number of waves, half wavelengths in between. It's impossible for this thing to end like right here, right? It's impossible for it to start here and then keep going and end there. So there has to be some number, and that's always how it's going to be. When you're dealing with standing waves, it's impossible for them not to end at the point you're holding on to, right? So it always has to have some number of half wavelengths. An interesting idea here is the number of nodes is equal to n minus 1. So the number of half wavelengths minus 1. Well, first of all, what is a node? A node is a point where the wave equals 0. Okay, so what we're going to see is this wave, in fact, equals 0 right here, right here, right here, right here, here, and here. Okay, so maybe off just a little bit, but the idea is those are considered nodes where something hits 0. This is going to be important later when we look at where electrons actually are, because we're going to look at probabilities ultimately is what we're going to look at. So a half wavelength is an important concept. Because we are limited to certain orders, these right here, we're only allowed this number of half wavelengths for each of these. This is what is going to lead to the idea of quantization of energy. Because we have these standing waves and they need to be very specific numbers, they're very discrete, we have to have specific quantization, meaning we have specific discrete energy levels. And that's ultimately what this idea of quantum mechanics is all about, where you have to have like fixed energy levels. You can't have a 1 1/3 wavelength. It doesn't work like that when we're dealing with standing waves. And that's really what electrons are dealing with. Okay, so quantization of energy is going to be a really important part of this chapter. So let's talk about this idea of, this is a black body radiation. So black body radiation, if you picture a coil like on a stove, for example, or some piece of metal, right? So if you start with a piece of metal, it's black. If you start to run some current through it, so there is some resistance, so it starts to heat up a little bit, and you put your hand over it, now don't touch it, but you put your hand over it, you're going to notice some heat. Okay, so when the object is black, it's actually giving off some IR radiation. You can't really see anything. You can just, so color, I should say, and then radiation. When it's black, it's giving off some IR radiation. Infrared radiation we can't see, but we can certainly feel because it's how things heat up. What happens first is you might see like a slight red color. That slight red color, well, now we're moving into the visible spectrum. Okay, so and if we continue to heat that object, right, that piece of metal, it goes from red to like orange. Right, and that orange, it's still in the visible region, but it's getting hotter. And then it goes to yellow. Once it gets to yellow, again, we're still in the visible region. It's getting even hotter. And then eventually it reaches white, which is all of the colors combined essentially. And that is going to be the hottest. Like, oh, something is white hot is because of that color. If we kept going, it would ultimately go to black again, or it might actually remain white. It would be visible, but it would also give off some UV radiation. So that's the idea behind black body radiation, is just put a current through something and to see what we actually have. Well, the concept here is if you continue to heat something up, eventually what you're going to see is you're going to see just keep giving off radiation, keep giving off radiation, keep giving off radiation, and you're going to see more and more and more wavelengths until the point where it's giving off UV radiation. So black body radiation and the ultraviolet catastrophe, if classical physics held true, and by heating something up, eventually you're going to produce UV radiation. Ultimately, what you end up with is in the situation where you're not going to see any light, and what you're going to see is you're just going to get UV radiation emitted from just regular objects, regular everyday objects. That's dangerous for a number of reasons, but ultimately what we find out is actually that's not how this stuff works. And that comes to the idea of Planck's theory of quantum mechanics, Planck's theory. So Planck's quantum theory. Planck basically looked at black body radiation and said, all right, heating a coil. So coil, again, that coil should just be a black body. Again, black body is a fancy word for just saying putting some heat through something, right? It emits heat. Okay, so we know that that's true. You know, showing no light. And then eventually red all the way to white. And again, classical theory is going to state that the energy emitted is just this continuous energy level all the way up until we have way too much UV radiation and everything is essentially emitting. But what Planck basically said is, no, that's not true. What's going to happen is Planck basically said, all right, what's happening is an atom vibrates in hot objects. With a specific energy. So instead of emitting all of the energies, with a specific energy. Okay. And then it's going to release small packets or small bursts of energy. We call these quantum or individual photons. And that energy of a photon is what we're interested in. So he developed this idea, well, the energy of some quantum or photon is equal to Planck's constant times the frequency of vibration of that radiation. Okay. And Planck's constant, you will be given this, but it's important to understand where it came from. Planck's constant is 6.626 times 10 to the negative 34 joule seconds. 6.626 times 10 to the negative 34 joule seconds, okay? Ultimately, what this led to is, well, if things are vibrating at a very specific energy and they have specific energies associated with them, energy is going to be quantized. Okay, so energy is quantized, energy is put in very specific buckets. It's allowed to make certain jumps and it's not allowed to make others. So that's the first concept of quantum mechanics, that essentially energy is quantized. You don't need to know anything other than the fact that energy has to have discrete energy levels. It's not allowed to be a variety of different ones. It's very specific ones. So that's where the idea of the photoelectric effect comes in. So the photoelectric effect is a great way to look at this. So Planck set about and said, all right, so here's the idea. I have some metal surface. Metal surfaces have a ton of electrons on them, and they give away electrons really easily. Okay, so, well, they give away electrons. They're just floating there. They don't belong to anything. Nothing's really binding them there. And then we're going to attach this to a voltmeter. And at the other end of the voltmeter, we are going to have a detector. And this is a metal. And this detector is going to be positive in nature. So if I lose an electron over here, which is negative, and it jumps up to the detector, my little voltmeter is going to ding, and I'm going to know that we essentially detected something. Okay, so the idea he had was like, so he said, all right, so if energy is quantized, ultimately what I can do is low energy light. So if I hit this with a red wave, if I hit it with a ton of red energy, so the two ways of looking at this is the classical look and the quantum look. So remember, classic means continuous. I don't think I spelled that right, but whatever. The quantum is quantized, or yeah, quantized. With the continuous means if I pound it with a bunch of red light, I'm going to get some number of electrons to come off. So for my red light in a classical look, what we're going to expect is a couple electrons. But in quantum mechanics, we should get 0 electrons or no detection of electrons at all, because the energy of the red light is not strong enough. But if we hit this thing with purple light, which is higher energy, again, high energy, and the red light is low energy. So if we hit the purple light or violet light, what we'd expect is we are going to get a lot more, lots of electrons, and quantum is going to get lots of electrons as well. So what you find out is, again, we expect the electrons to eject. Again, they're attracted to the positive, and this actually does not occur. But when we hit it with purple light, this does in fact occur. So we do get detection of electrons for that purple light. And so we can take a look at this and we can say, okay, energy is quantized. But we can take that a step further and we can say, all right, well, if I know the wavelength, I know the energy of the electron coming off. So if I know that I hit this with a photon of 550 nanometers, I know the electron coming off is going to have a frequency or a speed of 2.96 times 10 to the 5 meters per second. And I don't know why that didn't show up. I tried to fix it, but it didn't work. If I hit it with purple light at 400 nanometers, I actually know the energy coming off. So what this ultimately led to is, because energy is quantized, because we know the energy of a wavelength, we can determine the energy of the photons coming out based on this equation. And of course, this is the important part. Energy is equal to Planck's constant times frequency. So again, the energy is associated with the frequency. So with that said, find the energy of a photon with that frequency and find the energy of this photon with that wavelength. Make sure your units line up. We'll do these together. So that brings us to the last idea, the line spectra in the Bohr model. So to further continue to talk about this, all right, we need to look at quantized energy. Is it quantized or is it continuous? And the photoelectric effect said actually it's quantized because we don't get ejection unless we reach a certain threshold. And now let's take a look at line spectra in this idea of the Bohr model. And the Bohr model is the next chapter, but let's take a look at what line spectra are. So line spectra and the Bohr model. Okay, so I think your notebook is just a little bit different than this. So actually, I'm going to pause this. Actually, I'm just going to go with it. It's going to be slightly different, but you're going to get the same idea. So let's take a look. So let's just talk about this idea of the line spectra and the Bohr model. So there's two different types of spectra that we're going to have. The first thing we're going to look at is an emission spectra. And I'm going to take a hydrogen lamp, which is essentially just going to have, this is a cell with positive on one side, negative on the other. And we have a bunch of hydrogen gas in between. And I'm going to apply a current to this. And when I apply a current to this, the energy goes through, this is like a fluorescent light bulb. We force energy through a gas, the gas excites, and we get energy out. So this thing gets a bunch of energy to come out. But of course, we can't use that energy like that. We have to collimate it, or we have to put it, we have to fracture it a little bit. So we're going to take this energy and we're going to put it through this slit. Okay, so this is our slit. And we're going to do that because it's going to collimate the light. It's just going to create a straight beam of light out of all of this light that's hitting this thing. Okay, so this is just our beam of light. So this beam of light hits a prism. A prism, when light enters a prism, the speed changes. And because the speed changes, it essentially divides up into a rainbow, and we have our detector over here. So ultimately, it breaks it into a rainbow. One side, I'm going to have red. The other side, I'm going to have purple, and we're going to have Roy G. Biv, Roy G. Biv. And in fact, I don't think indigo is a thing anymore, so I'm just going to say Roy G. Biv. There we go. We've got all the colors in between. So if this is a continuous spectrum, we should just see, if it's a white light and hydrogen is pretty close, we should see everything. But in fact, what we do see is when we look at the emission. So again, this is going to be the emission spectrum. So we're going to see all the colors of the rainbow. We see a bunch of discrete lines. We see red. We see green. We see blue, and we see purple. We see 4 lines, and that is it. I see a line at 410, which is my violet color. I see a line at 434, which is blue. I see one at 486, which is green. And I see one way down here at 656, and it is red. And when I say those numbers, what I mean are nanometers. They're all in nanometers. So we see some very specific colors, but more importantly is we see these little lines. That's all we see. We don't see a continuous spectrum. We just see those lines. Okay, so let's take a look. So that's an emission spectrum from hydrogen. That means that hydrogen is limited to those 4 wavelengths in the visible spectrum. It can be elsewhere as well, but in the visible spectrum, it's limited to those. Let's take a look at an absorption spectrum then. Let's see if it behaves the same if we're looking at, so we don't have some artifact from something else. So let's take a look at an absorption spectrum. So an absorption spectrum is going to work similarly. So I have, in this case, I'm going to have a white light. Just a black body. It's got all of the colors of the rainbow. It's just got it's got all the colors, okay? And this time what I'm going to do is, instead of exciting the hydrogen, I'm going to put a hydrogen cell in its way. So I have this cell filled with H2 gas. So the gas is going to absorb light, this white light that's coming through. And what that means is the hydrogen is going to absorb specific wavelengths, we hope, to mimic what we just saw. And again, because it's going to do that, we're going to take a look at the light that's coming through here. And of course, we always want to collimate it. So we're going to need that slit that we had. And that slit is going to be sent through a prism. And when we send this through a prism, what do we see? Again, we're going to see this wavelength, this detector, and we're going to look at the colors that we see. So we end up seeing a rainbow of colors. It's going to take me too long to actually do a rainbow. So we see a rainbow of colors, but something very specific that we notice is something is missing. And what's missing is at 410, it's a little bit too intense. At 410, at 434, at 486, and at 656, we actually see black marks. In fact, if I don't have it in your copy of it, I would take a look at, just Google absorption spectrum, and you're going to see that it's missing those things. So what that means is hydrogen likes those wavelengths. Hydrogen is quantized for those 4 specific wavelengths in the visible spectrum. If we excite it, it emits there. If we absorb it, it absorbs that. So it's missing in the color on the other side. All right, that's good. That's most physics we're going to have. We're going to get into some, well, I lied, that's not true. We're going to take a look at the Bohr model and kind of what that leads to, but this is a good place to stop. Well, this is the end of part 1.